if it's in-house, go Paul. Take it away.
Hey, welcome back to the ultimate day of Friday. We have a houseful session today as well. And then Pablos will be co-chairing the session if he's online, and I'll be chairing the session as well. And I would like to welcome, this session consists of the developments related to dynamics, physics, DA, as well as coupling, basically. And I would like Bill Ramstrom, Lou Kramer, et al. Take over from me.
Thanks, Gopal. Today I'm going to be talking about the HAFS multiple moving nest work that we've been doing. So there was a good talk by Lou yesterday going through a lot of the results from the HAFS basin scale testing with this functionality this summer. So I'm going to talk about some of the other aspects of this work that has been going on and some proposed things for the future. So the main ideas we're going to look at, touch briefly on the forecast accuracy, but Lou gave a lot of the in-depth details on that. Then I'm going to spend some time talking on the runtime performance, runtime efficiency of this, and how that will start to look as we think about moving towards operations where we can achieve some savings on CPU resource as well. And then look at switch gears and look at some the meteorology of a couple of different cases. One, the Hurricane Helene inland flooding, and how there's a couple of different potential solutions that we can use particularly from the basin scale, some just from modeling that we might be able to use to examine those hazards and give some clear warning ahead of time. Do a little bit of a look into the case of Kirk, Leslie, and Milton, which we're seeing here on the right. So, this was a case where we had 3 storms that we were simulating at the same time. Kirk moving up into the mid-latitudes in the middle, Leslie sort of moving through the MDR, kind of struggling a little bit, then Milton, rapidly intensifying in the Gulf. Finally, if I have time, I'll talk about some of the runtime optimizations that we performed this summer to fit into some of our reservations for the HAFS. My timing last night seemed like that might not fit, so may have to just ask me about it later if you care about that. So in terms of the basin scale and multiple moving nests, about a year ago, we finished getting the multiple moving nest functionality running, so we can do, we've tested now up to 6 parallel storms, depending on the amount of compute resource we have available. One of the interesting things is the FE3 architecture from GFDL allows these multiple nests to run concurrently in a much more efficient way than HWRF did. They do that by the boundary conditions are actually extrapolated one time step forward so that the nest and the parent can integrate at the same time. And so that gives us a lot more efficiency than was possible with HWRF. During the summer, the HAFS, as we heard yesterday, we were able to run 3 parallel nests based on the compute resource we had available. And we saw, just highlighted here, some of the accuracy improvements we saw in terms of track and intensity. So, given that those accuracy things have already been talked about, I'm going to go through a couple different ways of characterizing the runtime performance, the efficiency of these. These tests were all conducted on Hera, so they're all sort of apples to apples in that sense. And we looked at 2 different configurations. One is this large basin scale, which is the 125 by 62 degree, and I'll show that in some later slides. Then another set of tests were on the parent configuration from the HAFS-B, which is a 75 by 75 single storm configuration. And the point of these is to demonstrate, number one, that the multiple nest scale very well, and then to start to look at, how we could make trade-offs if we want to fit into a particular operational window, if we want to go somewhere in between these 2 sizes of a basin. So just a little more detail here. These are approximately the same, size of the scale. So on the left is the basin scale, which is a little bit over 2 million points, about 2,000 by 1,000. These are both at 6 kilometer resolution. Then on the right is the HAFS B configuration, the 75 by 75 storm center. It's about 1.4 million points. So to do a comparison here, down at the bottom is the HAFS B single storm. These are from Andy's real-time parallel from this summer. So this was a number of the single storm cases run on HERA on 2,100 cores. It worked out to be about 5,000 core hours to run those. Then we compare that against the HAFS-M basin. So those scale up from 1,900 cores, then we add 400 cores for each additional nest that we added. So the real-time experiment, we did a lot of the runs in the 1 to 3 nest cases. Then Lou ran some 4 and some 5 nest cases just to help fill out the scaling. And what we see is, as a factor of how much how many core hours are used for the HAFS B, that the 1 and 2, because of the much larger basin, use somewhat more CPU resource. Then at 3, we start to achieve some efficiencies because it's not increasing as steeply. So at 3, we're just under the amount that it would take to run 3 single storms, and at 4 and 5 storms, we're having a CPU resource savings. So a different set of comparisons I ran a little earlier in this year were fitting a number of moving nests into the smaller base, the smaller parent of the HAFS B. We tested 1 to 4 storms, again, 126-hour forecasts on HERA. And what we see here is that the overhead compared to one nest is something around 10 to 16% as you add the nest. So it's pretty efficient run time. And I won't go through all the numbers, but the gist of this is 4 moving nests inside that parent is about the same amount of CPU resource as 2 single nest runs separately. So another way to save some resource and fit more storms in. Changing pace a little bit to talk about a couple of the cases that were notable from this year. A number of people have discussed the Helene inland flash flooding. So we have some of the radar plots of observed rain on the left and some of the figures from individual rain gauges, a number of them above a foot or even above 20 inches of rain. And the orography that was run in the 6 kilometer parent. So we see, the areas that obviously we expected to have a lot of the flooding in. So I took the 126-hour total accumulated precip from 3 different runs, starting on September 24th at 0Z, the 12Z, and then the 25th at 0Z. And we see, the yellow is about a foot of rain. So there's some differences between each of these runs, but at the same time, they all are indicating, really extreme rainfalls in those mountainous areas in each of the timeframes. And, I think, for instance, when we were listening to the map discussion that week, John Cangalosi from NHC was calling out, I think on the Wednesday morning, that NHC had already identified that they were concerned about the flash flood risk there. So we can see, this guidance also supported that sort of risk. So one of the things that I was thinking about as I looked at the terrain, terrain's sort of a way to look at where maybe the risk of flash floods is, but the terrain data set actually has a lot of different parameters in it. There's something like 10 different ways that they look at slope of the terrain and the actual elevation. But this one I thought was a measure that was really interesting to sort of characterize the flash flood and mudslide risk. And this is the standard deviation of the terrain. So within each 6 kilometer grid cell, this is how much the terrain the standard deviation of that terrain. So in some of those places in the Western Carolinas, it's, over 200 meters in there. And I marked on here the approximate locations of some of the places that we saw in the news that had some of the biggest impacts from the flooding, Asheville, Blowing Rock, and Chimney Rock. And we see they're right in these areas. So one of the ideas would be, perhaps we can make something sort of akin to some of the convective indices that you have, where we would just say multiply rainfall versus some of these terrain standard deviations, so that there'd be sort of a heads up of which geographical regions are, at risk of this. So presumably the weather forecast offices locally here understand, what the terrain in their area is, but for sort of a CONUS sort of view, this would help focus that in. And also something like an international desk, you could generate this over the whole hemisphere. So for instance, with Tropical Storm Sarah down in the Central America, you could start to focus in on which areas are at particular risk when the rainfall intersects these sort of terrain features. One other item that is a possibility with so we have multiple moving nests are enabled, but another potential thing that is possible that runs in this configuration is you could also add a static nest and still have several other moving nests. So something, where NHC identifies this several days in advance that this geographical region is at risk, where it's, not just the landfall location, we could consider adding a static nest over there for a bunch of these HAFS runs, so that they could focus in at higher resolution of, what's going on with this orographically enhanced rainfall, and really focus of, getting more local warnings. So this is something that if people are interested, we should talk about how we might build a workflow to make that happen. One other feature to talk about was, as I pointed out earlier, the Kirk, Leslie, and Milton case. So Lou showed this diagram a little bit the other day, which was the Sarah Ditchek's graphics of, which storms are producing the most enhancement of the forecast, and this is for intensity. And what we see is one of the main contributors here was Hurricane Leslie had a much better intensity forecast in the HAFS-M than it did in HAFS-B. So it pulled up the lifetime intensity forecasts from HAFS-M on the top, HAFS-B on the bottom. And what we see is, the HAFS-M did a much better job at the initial times of not over-intensifying Leslie. So at this point, we had Kirk as a very strong storm off to the north. So the outflow is probably being better resolved in HAFS-M by having that at the right intensity, by, running at higher resolution. And then later in the storm evolution, the HAFS-M again also had a little bit closer to the actual intensities, particularly sort of the lower part of the envelopes there. You can see HAFS-B had some that got very weak, closer to 20 knots, 20 to 30 knots, whereas the HAFS-M kept them sort of 40 knots or higher. So this is sort of one of the major contributors to the intensity performance that we saw this year. How much time do I have left? 2 minutes. So I'll just do a real quick run through. We did a bunch of runtime performance optimizations this year also to get the HAFS basin running in the reservation, particularly on JET. So there were two different tacks we went at. One was reducing the memory footprint, because we did have pretty restricted memory on JET, and then also parallelizing some of the pre-processing tasks to fit into the time windows. So the main one that was really important to do at the beginning of the season is we found that the static surface data at high resolution that we were reading in, as we went to the basin scale, that file grew. The amount of data that we had to read in was 13 different variables. And then for that large domain memory footprint, ended up consuming about a gigabyte of memory per process. And when we look at what was available on JET, there's only about 2 and a fraction gigabytes per core. So we're using an awful lot of the memory on just the static data that really isn't being used immediately. So what we ended up doing, in the interest of time, I won't really go through all the details, but we cut out a section of, like the green section indicated there, just somewhat larger than the nest of that static data, and we're able to really reduce that memory footprint. Some of the other things we did was parallelizing the lateral boundary conditions. That also helped speed up the pre-processing. So in summary, what we're seeing from the multiple moving nests in the HAFS basin is some really good track and intensity accuracy improvements, days 2 to 5, and a lot of compute efficiency gains when we look at configurations in the 3 to 5 storm range. Then it's sort of from the science perspective, we have some ideas of we could use static nesting to focus on some of these inland hazard areas, as well as potentially generating some new diagnostics to try to focus on the hazards and flash flooding. Those those diagnostics some simple ones would just probably be a post-process thing. Not a lot of work to generate those in terms of engineering or compute. And then finally, what we're looking forward to after we get basin implemented will be, starting to move towards more global parents and nests in several basins.
Thank you. We'll get back to the questions at the end of the session, and I would invite Franklin and Andy for the next presentation on physics, HAFS physics.
Since it's a tag team only for 9 minutes, I can make sure leave some time for Andy to present.
Hold on 1 second. We're still doing that online.
Okay. So this overview of the physics development for HAFS. I'm Fanny Yang from EMC, and Andy will give a presentation on the HRD side. First, I'd like to thank all the physics developers at EMC, HRD, and also the community, and of course the funding support from NWS and also our program offices. And next slide. Oh, I have this one. Okay, that's better. I control myself. First, I want to say we have a monthly physics meeting dedicated to HAFS. Currently, I have participants from EMC, HRD, or sometimes also from university. Really focused on the HAFS physics development. If anyone has interest, let me know. I can add you to that meeting. I think it has been very productive in the past few years for HAFS development. First, I give an overview for the physics development, not only for HAFS, also for the entire UFS based applications. You can see on the different side that we have our R phase, the equilibrium and quality model HAFS. On the right-hand side, that has the global applications, including the ensemble forecast system, the medium range GFS, and also under development the SA phase. We also have included the whole entrance model in this suite. And the physics development, there are two purposes we have been trying to focus on. One is really the unification of the physics parameterizations. Not all the physics is scale well so far, but wherever feasible, we try to unify them among the applications, really aimed to reduce the R2 transition the time, and also reduce the cost of operational maintenance. And another major focus is we try to reduce model systematic bias and improve model forecast scales. This is the overview of the physics transitions used in current major UFS applications. You can see on the second column for the global model, we have achieved the goal, unify all the physics parameterizations. On the third column is the HAFS version 2, HAFS A and B, because then it's diversified for the microphysics. Compared to HAFS and the global application, the only difference really is the non-surface model, the NOAA non-surface model. We are in the process of install the NOAA MP or actual testing the NOAA MP for the HAFS application. I have one slide to show that later. And there are some variations in terms of how you tune on some of the specifically for the HAFS application, like convection scheme and the PBL. And as I mentioned earlier, not everything is on scale well at this moment. For AQM, this version 7 uses the GFS version 16 physics, but the version 8 will be unified with the GFS version 17 physics. If let's summarize some of the major physics changes we made in the past few years. Like the microphysics, we switched from the GFDR microphysics to the two-moment Thomson microphysics. Thomson used to be more popular in the regional model application. This actually is really the first time used for the global applications. We found the first is really computational instability issue. Then we developed the so-called semi-Lagrangian segmentation for rain and gravel, and also improved the cloud radiation detection tropics. We replaced the NOAA non-surface model with NOAA MP, and developed a new scale, small scale quantum wave, and also turbulent orographic and foam drag parameterization. Update the science convection and the probabilistic the mass flux parameterization, and also have the new stochastic physics in ocean, land, atmosphere, and new positive definite tracer observation scheme. We also now the areas of cloud radiation capability is functional of also has been turned on in some applications. We also develop so-called fractional grid for global couple application. Many other improvements include cumulus convection, boundary layer, ground track. One of the changes, first element for the global model, and also we testing the HAFS application. Those also in blue colors actually have already been included in HAFS version 1, version 2. And this HAFS version 2, the physics scheme, and many of the developers or speakers in this meeting have mentioned, I don't need to go to the detail, that's many of these schemes has the star attached to them. That means has been updated from version 1. And also shows the difference between HAFS A and B. What's the physics difference is mostly like the boundary layer use different tuned parameters. The different time step for Thomson scheme. Also, of course, the ocean model different. One is MOM6 and one is the HICAM. This is a laundry list of what we have been doing for the physics development. Some of them including the version 2, version 1, some still under development for future application. Also want to highlight some of the collaborations with the community, like NOAA land surface model. I've been working closely with Bill, especially at HRD. We have the 3D TKE PBR scheme, Professor Pinzu from FIU on implementation yesterday. It's been funded by GTTI. I need to point out Chandra for really help this get this transition to operation. And we have been also testing the TT convection scheme, and we'll probably have more on this. We've also been collaborating with Xiaoming. Xiaoming was a HRD developer, now is a professor at the University of Alabama, Huntsville, was funded by WPO on the boundary layer scheme development. Also, we have the cloud overlap, and this TTC, as Kenson mentioned earlier today about this project. We have also been developing in-house total turbulent energy based EDM PBR scheme. I have more details on this. And also idealize the HAFS framework to facilitate testing and improve the physics dynamics scheme and testing MY and EDM PBR scheme in HAFS. A few other I should mention, also has been happening, but under the radar, like test the impact of update vertical velocity calculation on HAFS and tuning the cloud microphysics parameters, the impact of scale adaptive convective cloud compensator and its interaction with radiation, a new scheme for computing maximum mixed length in PBR, also sensitivity of the HAFS to update FSG dynamic core and dumping scheme. Actually, I missed one. We are also testing the GFDS microphysics version 3 in HAFS and also GFS. This example, like this idea, that's the framework mostly developed by Weigo1 at EMC. Its utility, you can really use this to understand some of the fundamentals, because when you run the full model, sometimes you don't know what's the cause and effect relation. With the simple framework, you sometimes can understand when you change a parameter, what's the real cause is. It has been used in real case for test and evaluation. This total turbulence energy estimate for been tested in GFS developed by Jung Han at the EMC, and for GFS for 1 season. The bottom line is it has probably close performance to the current TKE estimate. For the major difference between the TKE and TTE is it's including both the kinetic energy and the potential energy to avoid a limit of the richest number that turn off the turbulence in the PPR. I mentioned the non-surface model development. Let's just demonstrate that it's functional. It's working now in HAFS. Actually, it's not a technical issue being overcome between Longqian Yang at EMC and worked with Bill at HRD. And with this capability, we're in the future, like you can even couple the off-hydro everything to the non-surface model to really capture better after the landfall of the storm, the impact of heavy precipitation. This one slide for the Xiaoming about the development areas framework and facilitate the development of hurricane models, especially over in high wind situation. Sorry, I did rush. I cannot. I hope I have more time, but I only have 9 minutes. It's really, I'm doing this just not just for the developers. So what you should hear from Xiaomi is you can say use this framework and can really capture some of the deficiencies of the current PBR scheme, like the M1 EDMF PBR scheme. It underestimates the momentum stress in the cloud layer. Hope I still leave a few minutes for your son.
Thanks, Lin. Yeah, so I'm going to focus specifically on some of the development activities that we did at AML, and now that I've been finishing in my current role with INSEP for HAFS-B. I'm mainly focusing on convective scheme evaluation, and kind of the motivation for this is obviously we want to improve the skill in HAFS, but also get diversity between HAFS A and B, since we're looking to replace HRF and HMON and in the consensus. So we evaluated a couple of different schemes, including the RAS and TDG is the one we've been focusing on. And so in some of our retrospective testing we did, TDG is the one that seemed to produce the best track performance. It's kind of not too surprising, with some of the testing like the DCMWF and others have done. But there was a negative intensity bias, and so that's something we've had to work toward addressing going forward. And like I said, the PPs pretty much showed consistent track improvement out to days 3, 4, and 5. And so that was sort of what we selected for our real-time experiment this summer. We did notice when we were doing these tests, there's some pretty big differences in convective structure, kind of what you'd expect. So you have the default HAFS-B on the top left, and then on the top right is with the prognostic scalar closure, or prog sigma, which is, I think, been implemented since in HAFS operationally, and then the experimental RAS and TDG on the bottom. And you can see that for TDG, there's a lot less light precipitation, maybe a little bit more dry air. And we saw that too with the cold pool structure. overall, it's kind of a similar structure, but the RAS and TDK seem to have these stronger cold pools with stable air on the upstream side. And so it seems like there's some differences in how the updrafts and downdrafts were parameterized that were leading, consistent with some of the intensity biases we saw. So I've also been working with Jung-Hoon Shin at EMC. He's been helpful in doing some testing with TDK and it's kind of improving it beyond just sort of the baseline scalable version that we got from NCAR. And we saw some promising results in initial testing. And one of the things that we found was that in our retrospective testing overall, TDK did a lot better, but there's, the results were kind of muddied by Philippe, which is one case from last year where we had some really huge errors. And if you remember, that was one case where, the storm was, some of the models were trying to recurve it, intensify it, ended up staying weak, going west for like 10 days. And so it was really biasing the track stats and the intensity stats. So Jung-Hoon did some work that found that basically tuning the detrainment coefficient improved Philippe and improved overall stats as a result. And this is consistent with some of what was done in the scalar SAS scheme as well. TCs are really sensitive to that dry air detrainment. We saw this this year with Helene and some of these other cases where getting that dry air interaction correct is really tricky. And so in our retrospective testing we did kind of prior to the season, we saw that including this modification to the detrainment in TDK, it basically led us a pretty good improvement beyond just the baseline version. And so this is something that we incorporated into the real-time testing that we did this summer. And as you saw my talk yesterday, you saw that we had very promising intensity results with pretty solid improvement overall over the operational version. And so this will be something that we'll be considering for maybe a future upgrade. I don't know if it'll be next year or the year after, but as we look towards the future with trying to get the diversity between the two versions, that convective scheme is really a good way to do that. And also something that will hopefully be incorporated in the ensembles as we look for ways to generate both track and intensity spread that's reflective of all the possible outcomes. So thank you. We'll be happy to take questions later.
Thank you, Andy. It's right in time. Yeah, next we'll go to the PA updates, Jason and Daryl.
Okay, thanks, everybody. Oh. You ready? Good. Okay. So I'm presenting this on behalf of Daryl Kleist. Worked with him and Zach to put these slides together, looking at the progress over the past couple years since the HAFS IOC. So it's roughly divided between the initial IOC capabilities, what we had going in and what was developed and the initial release of HAFS. We had some additional developments for 2024 for HAFS V2, and then there's some ongoing and future developments, specifically focused. A lot of it is on the initial imbalance problems that we've talked about through the week, and I'll offer some concluding thoughts. So going into the IOC, on the left, we talk about vortex initialization. Anybody that's known me long enough knows that I am not a big fan of vortex initialization, but the cold hard facts are that both vortex relocation and modification do help the forecast still, and until they don't, we will continue to have it as part of the DA system. So we borrowed this from HFIP and HMON with some changes. Like I said, it involves both relocation and modification. They're both currently turned on. And it combines the HAFS prior storm perturbation with the background from the GDS environment. On the right, in terms of the data simulation basics, we have 6-hourly cycling. The IOC used 40 E and VAR with GDAS covariance. That's different than HFIP, which used 2D E and VAR, and sometimes it used GDAS, other times it used the HFIP cycle covariance. I'll talk about this a bit more coming up. We, like HFIP, leverage jobs using GFS with some additional mesoscale observations, including reconnaissance, NexRad. We added METAR. I had a Precip Grand Challenge proposal that looked at the impact of assimilating METAR mesonet observations in HFIP, and it improved the landfalling TCs quite a bit. So that was added in HAFS. And also some AMVs that are not assimilated by GFS. So we upgraded to 40 E and VAR. this is again using GDAS, but the orange line here compares 3D with GDAS to the blue line, which is 4D. This is relative, I believe, to, yes, relative to HWRF scale. So track, they're both quite a bit better. You get a little bit of a bump with the 4D. And intensity, it's a little bit mixed, but there is a good improvement at the 72-hour lead time. So 4D and bar better accounts for the time evolution of what's going on in terms of the covariance within each cycle. So, there should be some inherent improvement there. And there is. It's just, not a huge bump, but it's definitely incremental in the right direction. So that was kind of the big DA upgrade we had in the IOC. We've had several more in HAFS V2. One is hydromedia relocation. Now, this is part of the VI package, but what it allows us to do is get our initial fields to be more realistic. So if you look at, for example, on the left, you have the HAFS V1 analysis reflectivity, and you can see it doesn't look realistic compared to the TDR reflectivity in the middle. I'm not sure what case this is. It's a generic example. It doesn't really matter what case it is. But with the hydromedia relocation going into HAFS V2, you can see we have something that looks realistic. Now, it doesn't have to look exactly like the TDR, but the bottom line is that we have something that's physically more realistic. And indeed, it helped the intensity scale. So you can see across more times than not, you get a bump in intensity scale when you turn this on. And that's a decent sample, over 400 cases. So this was something that we have now that we did not have in the past, and HWRF never had it either. We also had some upgrades. One of the components of vortex initialization was that it uses a composite vortex in certain circumstances. And in HAFS V1, we were using a HWRF composite vortex. We had not yet built the HAFS composite. And so that caused some problems, some imbalances in the initial conditions in some certain cases. In this example here, this is a Westpac case without data assimilation. And you can see the blue is the best track. The red dots are the SLP initialized due to using this HWRF composite. And you can see they're not right. They're way too low. So when we move to using a HAFS composite, which is in V2, you can see on the left, we actually have two different composites. We have a weak and a strong composite. And the resulting SLP in the initialization is from the black dots. And you can see they're a lot closer to the blue line. They're not perfect, but they're certainly a lot better than the red dots. So we're moving in the right direction. And so the points here is that we are getting improvements due to improving vortex initialization. And those are examples too. These are just a few of them, but we're still getting stuff. We're still getting positive, moving in the positive direction through working with this VI package. So that's certainly encouraging, and I think that work will continue as long as it gives us those incremental improvements. Now, on the DA system itself, we had some upgrades to the localization. So covariance localization constrains basically how spatially an OB will influence a given region in the analysis. Large localization will allow the OB to affect a large area, a small area. Hurricanes are multi-scale though, right? So different OBs should be affecting the analysis differently, right? You should be affecting the large scale and the small scale with observations. Historically, HWRF and HAFS V1 only had a single covariance localization. There's no multi-scale component. OU developed scale-dependent localization, which decomposes the background in the ensemble into multiple scales. And so this was developed and applied to HAFS. They gave a talk that included this previously. So here's just an example of what this looks like. So on the left, we have analysis increments with a single small scale localization. In the middle, you could have increments with a single large scale localization. On the right, the scale dependent localization. So this is just one example with the single OB test. This was put into HAFS V2. The results were neutral. So it did not dramatically improve the forecast, but it does set us up to be able to tune and to get this, move it in the right direction in the future. And I think this is important because I've seen plenty of results in the literature implying that when you do properly account for these multi-scale nature of observations, you can get much better results out of your DA system.
So it certainly allows for these, improvements in the future. Now, moving on to the future of HAFS DA developments, I really want to focus on the initial imbalances. And one way we're doing this is looking at IAU, not AIU. That's a typo up there. It's IAU. So what IAU does is it takes your initial increments and it applies them as a forcing function in the model over, in this instance, so the first 3 hours. This is a way to deal with the fact, especially in the inner core, that you can have strongly asymmetric increments that spin down, they result in crazy gravity waves and all kinds of weird things that go on. We've seen these, people have been talking about them, but the inner core just doesn't look right in the analysis. So with IAU, you're at 0 hours, it's just vortex initialization. So it's fairly symmetric, right? And then you have a forcing function applied over these 3 hours. And so you don't get these imbalances as much. And so what we see with IAU over a very large sample, over 1,000 cases, is that up to 5% improvement in the intensity forecast. So it's another incremental improvement in the right direction. It's a little bit bigger than going from 30 to 40 in bar. So certainly that's a good sign. Another thing that we are testing right now is this spectral filter. And this was used in HFIP. This is something that came from discussions between myself and Henry Winterbottom. And it was, again, it's an ad hoc method, but what we did was we've known that these very strongly asymmetric analysis increments can cause spin down, can cause problems. So we decompose these into polar space, into a spectral space, right, in within the inner core, and we take the low order components only. So for AH4, I believe we took just the wave number 0 for hurricanes, right? So just the symmetric component analysis increments. You're basically smoothing them out in essence. In this example on the left, this is just a generic example where we have large negative and positive increments. I think this is 0 plus 1. And so in HAFS, we didn't have this yet. This is just being tested in research mode, right, so far. And we've tested 0 through 2, so up to wave number 2. And the results are on the right. So when we apply this filter to hurricanes, we get roughly up to about a 5% improvement in the intensity forecast. When we add IAU and the filter together, the improvements are up to 10%, and they are through all lead times. So certainly, again, this is something that we can use going into HAFS V3, for example, to deal with some of these problems we've been having in the recent versions of HAFS. Another tool in our chest is mesoscale error covariance. This I stole from Chu. This was from Hurricane Lee. It's on the left, we have this typical problem we have with inner core data, where we're using GDAS covariance. You have these pressure lobes, the wind fields can look wonky. It doesn't look like a hurricane. On the right, we have 6 hours spun up mesoscale covariance, initialized off GDAS, and then ensemble relocation is applied to that, and voila, we have a hurricane, right? So I don't know at what point we'll have the CPU capacity to run a HAFS ensemble over the sufficient area to get this done in the Atlantic, for example, when we have recon. But certainly it is a tool that should be further tested and evaluated. And when we have the CPU, we should definitely implement it. Our research partners, University of Miami has a WPO OBS proposal that was funded, and they have the JTTI as well with the multi-institution. And one of the things they're looking at is the observation errors. It turns out that observation errors are really, really important. And especially as you get to the inner core, things get really complicated. And there are theoretical values that you should have for observation errors. It's a ratio of your observation error to your observation space spread in your ensemble. And without going into all the details here, they should balance each other out, right? And if that ratio is proper, it should be about 1, right? So it turns out that they weren't balanced in HAFS, and I think we feel like it was causing some problems. So we tuned some of the observation errors. I don't have the results for that, but I will say that on the research side, they did notice that the analysis RMSEs for the constant state are substantially lower when the errors are better tuned. I will also say that the errors are situationally dependent. The errors you need to have for the inner core for like a major hurricane are not the same as the errors you should have in the environment or for a tropical storm. If you think about what's going on in the background, the gradients are much stronger, your representativeness error is much different, and your observation variability is much stronger with the inner core of a major hurricane. So this is a challenge we're going to have to address in the future and how to deal with this. University of Miami is also looking at some experimental data bringing in. They're assimilating IRAP wind profiles, the super obs. Zorana talked a lot about IRAP a few days ago. This is being tested in terms of assimilation in HAFS. They're also looking at assimilating, expanding the ground-based radars. For example, these radars down in the Lesser Antilles. If, you know, in some future world, if we're bringing in additional ground-based radar data, that might change, for example, our reconnaissance CONOP. Because we're bringing in, you know, radar data, we might not need to fly there. This is very forward-thinking, but it's an interesting question. More immediately, we're looking at the impact of buffer drop zones. Catherine Selwood looked at this. She had a talk on this, and you know, using these super obs has a few advantages. One of them being averaging local varying obs instead of using just a single ob that's not an average, that could not necessarily be representative of what's going on. And then also the variance within a super ob can help with QC. JEDI transition, just briefly, this has already all been outlined. There's been great progress. We've got a proof of concept. I'm running short on time, so these have all been covered by previous talks, but bottom line is we're making great progress on JEDI, including some interesting findings. This was also presented that the differences in interpolation between JEDI and GDAS can cause some big differences in terms of your forward model. So that is something that we are continuing to explore. And then finally, concluding, last but not least with the ocean, Kim Sook, I know you're happy. A lot of progress has been made on the ocean DA side, and we're getting analyses that look reasonable, assimilating the data that's listed here, but more importantly, using this, we're getting forecast improvements as well, as shown by the track and intensity skill here. So definitely moving in right directions, not only in atmospheric DA, but also in ocean DA. This is all really encouraging. So in conclusion, DA and HAFS has made substantial progress since the IOC. The improvements are occurring for vortex initialization, still an important component of the system, as well as observation usage and DA strategies. We got a strong focus on this initial imbalancing in the inner core, and I think we're going to have some implementations of some of these strategies going into the next, perhaps even the next version of HAFS, and then some further, more advanced developments, you know, are possible in future versions. And finally, ongoing work is focusing on improving the inner core data usage and the transition to JEDI, both for the atmosphere and the ocean. And that is all I have. Thank you.
Thanks, Jason. We'll follow it up by the ocean updates. Maria or Maria.
Good afternoon, everyone. My name is Maria Aristizabal from EMC Hurricane team. So first, I want to thank the organizers for inviting us to talk about the ocean and wave coupling in the HAFS system. So I would like to acknowledge my co-authors, Bin Lee and Hyun-Suk Kim, and the entire EMC Hurricane team. So I'm going to start with a very brief description of the ocean and wave components in the HAFS operational configuration. So as we know by now, HAFS comes in two flavors, HAFS A and HAFS B. So HAFS A is coupled to the MON 6 ocean model, while HAFS B is still coupled to HICOM. So both ocean models have a 112-degree horizontal grid resolution. For Moon 6 has 55 vertical levels, and HICOM had 41 vertical levels. For both models, the ocean initial conditions come from the real-time ocean forecasting system, R2OPS. And also, both models use the KPP profile parameterizations as a vertical mixing scheme within the upper ocean mix layer. So, yes. So in terms of the ocean model, we use the Wave Watch 3 model, but this is only used in HAFS-A. So HAFS-A is the only model that is coupled to the wave model. In terms of the coupler, we use the Community Mediator for Earth Prediction System, CMEX. And CMEX is the part of the system that is in charge of exchanging and interpolating the different fields from the different components. So I'm going to focus here in this sketch at the top, and this is only refers to HAFS-A. So this shows the different fields that are exchanged between the different components. So for example, from FP3 atmosphere to the ocean model, we exchange sensible and latent heat fluxes, long wave, short wave radiation, precipitation rate, and mean sea level pressure. And from Moon 6 to FP3 atmosphere, we exchange sea surface temperature and sea surface currents. Now, from FP3 to the wave model, U and B components of velocity are exchanged, and nothing is exchanged from wave 3 to any of the components. This means that at this moment, the wave coupling is only one way. Now I'm going to move into the real-time configuration. So the only difference, before I talk about the operational configuration, and this is the real-time. So the main difference here is that both HAFS-A and HAFS-B parallel are actually coupled to Moon 6. In terms of the physics, there are differences. For HAFS-A, the vertical mixing parameterization that we use is the energetic boundary layer parameterization EPBL scheme, and for HAFS-B, we're still using the KPP parameterization. So here in this map, we can see the different ocean and wave domains. For the ocean domain, we have three large study domains. So here in blue, you see the NHC domain that covers the NHC areas of responsibility, and we have all two large domains that cover the JTWC areas of responsibility, Northern Hemisphere in red and Southern Hemisphere in green. For the wave model, we have two domains in green, one that covers that large area of the North Atlantic and the other one that covers the Eastern and Central Pacific. So for the evaluation of the ocean and wave response, I'm going to focus on two high-impact storms, Hurricane Helene and Hurricane Milton. We have heard many things about these storms, but I will continue doing the same thing. So for Hurricane Helene, we look at the pre-storm ocean conditions. In particular, we look at the ocean heat content along the storm track. So here, from the interest of time, I'm only showing this figure for HAFS-A, but we obtained very similar results for HAFS-B operational and HAFS-A and B parallel. So we can see that the general pattern of the ocean heat content is very well captured in this area of the Gulf of Mexico and the Caribbean when we compare with the ocean heat content product from the University of Florida at the bottom. So during this time of Helene, we see that the loop current that there is this area of very high ocean heat content. It was intruding into the Gulf of Mexico. And you can also see that there is a 1 eddy that is about to detach from the loop current. For this particular cycle that I'm focusing here, all the different hubs have A-B operational and have A-B parallel, experience rapid intensification, and this happened at forecast hour 24. This coincided when Helene was entering this area of very high ocean heat content. So this highlights the importance of providing accurate ocean initial conditions for the HAFS system. However, for this particular cycle, HAFS was a little too aggressive in rapid intensification, and the RI event happened 6 hours earlier than the base intensity forecast showed. Right before the conflict of Helene, Helene was basically encountered by 2 sail drones and 1 glider. I'm going just to show here the data from 1 sail drone. That is shown here in the bottom map in blue. So I'm going just to focus for the water temperature. So in blue, in the blue, we can see the response, the surface temperature cooling that was obtained by the sail drone observations. Below, we see the sea surface temperature response by the different HAFS configurations. And what we can notice right away is that the rate of cooling is very well captured by the different HAFS. And this is great news, encouraging results. However, we see that there is a little bit of cold bias also from all the different HAFS. So this means that, yes, we are getting good results, but we still have room to improve the ocean initial conditions. So aside from the sail drone and the glider observations, Helene passed very close to an NDVC buoy that we see here as a blue star in the bottom map. And this NDVC buoy measured several wave parameters. So this was a great opportunity for us to test the wave coupling in the HAFS system. So I'm going to, here in the right side, you see the significant wave height, the dominant wave direction, and the average wave error. So we see that for all these 3 quantities, HAFS did a quite good job before the passage and after the passage of Helene. Also, there was a good agreement in the timing of the peak of these quantities. However, we see clearly that HAFS had a little bit of overestimation from these different quantities, specifically for significant wave height and average wave period. So again, very encouraging results, but we still have a lot to improve in terms of the wave coupling. As I mentioned before, at the moment, the wave coupling is only one way. So 2 weeks later, Milton, after the landfall of Helene, Milton developed and made landfall 200 kilometers south of the location where Helene made landfall. So during this period, there was a glider here in yellow that covered the period of both storms. So here the glider data reveal very interesting things. So first of all, before the passage of Helene, we see that the sea surface temperature in this area of the Gulf of Mexico was around 30 degrees Celsius. And this is shown as the red dots that show the temperature profiles. After the passage of Helene, there was a cooling in the sea surface temperature of about 1 degree. So now it takes about 1 to 2 weeks for the water column to bounce back and go back to pre-storm conditions. However, because Milton was coming on the way, the sea surface temperature couldn't recover and it continued to cool down, as you can see here in the yellow dots. And further cool down as expected after the passage of Milton, and you can see here in the cyan dots. So as we can see, we can argue that this continuous sea surface temperature cooling actually decreased the potential for Milton to experience rapid intensification before landfall. Another aspect that is really interesting that we can see here from the data is the continuous cooling, continuous deepening of the mixed layer depth that you can see here. So we wanted to see if HAFS was able to capture these physical processes within the water column. So we built the corresponding figure from the different HAFS configurations. And again, I'm only going to focus here on the HAFS A operational. So we can see that in terms of the surface temperature cooling, it was excellent. Great job, HAFS. You can see it's cooling. But in terms of the mixed layer depth, we see here, if you focus on the blue dots and the blue line, we see that HAFS is deepening the mixed layer depth too much compared to observations. So this means that we still need to keep exploring and tweaking the vertical mixing parameterizations within the ocean models. So this is exactly what I just mentioned in the previous slide, but this is another plot from the sail drone. You can also see here the sea surface temperature time series from the sail drone and the continuous cooling. And below you can see the response of HAFS, again, capturing this continuous sea surface temperature cooling. So after Milton reached its maximum intensity, it cooled down approximately 1.5 days before. And during this time, HAFS forecasted that Milton was entering an area of higher vertical wind shear, lower ocean heat content, and relatively sea surface temperature that was caused by the earlier passage of Helene. And the confluence of these three things caused for Milton to weaken right before landfall. So now I'm going to turn it over to Hyun-Suk, and Hyun-Suk is going to talk about the ongoing and future work. No, Hyun-Suk. Oh, I didn't prepare either. Okay, so I didn't prepare either. So Bin Lee has actually in our group has been in charge of the current future development of the wave coupling. So here, so Bin Lee basically has been running experiments with one-way ocean wave coupling, as you can see here in the top, and with two-wave ocean coupling. So as I explained before, right now is only one-way coupling between the atmosphere and the ocean. So he's experimenting with two different configurations. He did several runs of Hurricane Fiona, Ian, Idalia, and Philippe. So here are the results. And you can see, so in red, we have the two-wave ocean coupling, and in blue, we have the one-way ocean coupling. So we see that we have improvements for all different forecast hours. So these, again, very encouraging results, as you can see here. So this is the future work. I'm going to focus much of this, but basically the main idea is that HAFS is going to move into the three-wave coupling. So basically, three-wave coupling means all the different components talking to each other. Atmosphere passing fields to the ocean model, atmosphere to the wave, wave to the atmosphere, wave to the ocean, ocean to the wave. So this is the future for HAFS. So to conclude, so in situ observations during tropical cyclones are extremely good asset for us to evaluate the ocean component in HAFS. The upper ocean conditions, ocean heat content, and sea surface temperature during Helene and Milton were well captured by the HAFS system. Still, there are a lot of things that we need to improve, but very encouraging results. And the global observations show that the early passage of Helene cooled down the sea surface temperature, and so this basically reduced the potential for Milton to rapidly intensify before landfall. So this is a good example of, hurricane-hurricane interaction from the ocean point of view. And finally, to better simulate the sea interaction processes, wave coupling is essential by including additional steps of the wave properties, especially wave stress, that is important to modify to the modification of the momentum flow exchange between all three model components. Thank you.
Thank you, Maria. Thanks to all the presenters. We now have about, only about 5 minutes for, 10 minutes for questions.
Just quick, that seemed prepared. Very nice job. You did excellent job.
Thank you. We go on to the discussions.
We're already doing discussions. I started it because you were busy on your phone. I'm coming, folks. Oh, can you bring up the chat? He just has a hand. Oh, I'm sorry. I didn't. Sorry.
Lou, go ahead.
Thanks, Aaron. So this actually is a question for Maria and Hyun-Suk. Exciting work going on. I was wondering if you have had the opportunity to explore how the two-way ocean wave coupling impacts the wave forecast. You showed some nice results from the one-way. Particularly wave period, dominant wave period and direction.
We have not, Lou, but that is a very good point. So Bin Lee, that is the one running all these experiments, at first look at the traditional statistics, intensity improvements, track improvements, But we haven't had time to actually look at his runs and make kind of like the same comparisons that I show here with the one-way coupling. But definitely that's something that we will look at.
Just a follow-up comment. The aerial reconnaissance measurements of waves might actually be very valuable as a comparison point too. So thanks.
Thank you, Lou.
Yeah, this is Wallace at the Hurricane Center. Question for Bill on the basin scale. So I don't know much about HPC, but earlier we were hearing about the resources available in the development systems. It'd be nice to have a long reanalysis of HAFS at high resolution for a variety of purposes. I'm just wondering if the basin scale HAFS is it possible to create a reanalysis, and is that a good idea to think about that?
I think, technically, yeah, it is possible. And the nice thing of the basin scale is the consistent parent, makes DA and sort of reanalysis, make more sense. Yeah. I don't know about our actual resources do it, but I think it's a configuration that would definitely be well suited to that. Yes.
That's a question. Yeah.
Thank you. Yeah, one comment to Maria and Yunsuk. This is June from HRD and the SAMERS. So at HRD, in our annual Hurricane Field Program, we have 2 ocean-based experiments, Ocean Survey and our Chaos Experiment Lab mentioned. So we're willing to collaborate with EMC, you guys, to do model evaluation. We can also work together to design new flight modules to collect some data targeting the ocean model improvements. Just want to comment that.
We can certainly use the observation for data simulation first before you can go on the validation. but wave data simulation has not been built in yet, so definitely we can, certainly use for validations. So it will be coming on, but we have to do it to the wave coupling properly working, and there are a lot of wave properties missing at the current wave and coupling in the HAFS system right now. It's just even who brought up question about Lou brought up the question about the two-way coupling between ocean and the waves. We see a lot of subscale features by having two-way coupling. So it more like have a more higher vorticities and the energies, shifting and to the small scale now. So that seems to be close to the more reality. Definitely, we need that. We have to go with the two-way ocean side, but in the atmospheric side, we have to provide more wave properties in order to make a momentum fluxes adjusted.
Okay. Actually, it comes back to for the basin milestone HAFS. I think thanks for all these additional tasks for the scalability, adding more storms. Looks like the efficiency is pretty good. I think probably worthwhile to do another, say, test. For example, if we have 5 storms, compare these 5 storm moving nest against like a single resolution parent domain to see how efficient this configuration could be. Probably more useful information. I think another more like hurdle for us, I think, is the domain coverage right now, where we cannot configure a large enough domain to cover both basins. Basically, right now it's only one basin, maybe slightly more than one basin, but I think we need to try to explore why and how can we expand that domain to cover hopefully 2 basins, like NHC area of responsibility.
Yeah, I think I like both those ideas. Yeah, the first one of comparing it against something like maybe the T-shield sort of configuration, basically, right? Looking at what the performance of that would be, just to get that scaling. And then, sorry, what was your second question?
The one who was suggested to do the price numbers one single.
Right. Oh, and then the other was the basins. Yeah. So right, the limitation there has been the ESG so far, we think. But you know, some of those optimizations we did, maybe those were causing some of the problems we had. Like it might be worth re-exploring it and seeing what was going on. Because basically, we could configure bigger nests, we could construct bigger nests with ESG, and then the model would crash soon after it started. So we don't 100% know why that is going on yet. So yeah, it's worth some more looking into, because yes, it would be nice to make that somewhat bigger domain.
Lou, did you want to respond to that? Is that why you raised your hand?
Yeah, I was actually just going to sort of amplify what Bill said. Yeah, I mean, we can definitely look at a larger domain. And in fact, we have begun trying some experiments with a narrower, wider domain. So that would end up excluding some of the TCs in the Northern Atlantic undergoing transition, but capturing a lot more of what's happening in the East Pacific. One challenge we have with using a narrower outer domain, by the way, is that you just don't, I mean, there are a lot of multi-storm situations, but you just don't have as many occasions when you have, you know, 4 or more TCs only active in the Atlantic. It happens, and it's pretty exciting. But you know, I think I would sort of flip the answers to those, see if we can first explore a larger outer domain, you know, and then, you know, maybe start looking at some of the, you know, looking more closely at some of these efficiency improvements and improving that scaling.
Yeah, this is Xiaoming from the UH. So Maria, nice talk. So I have a question for you. So basically it's like you see the HAFS A and HAFS B using different, ocean coupling model, right? But meanwhile, they're using different PBO, the motion PBO scheme. So for that perspective, like, have you done a clean test just using HAFS A, but using the ePBO and the KPP, and see what's the main impact on the hurricane forecast, or also the ocean coupling effects?
Yeah, I've done it, and then turned out that I was expecting KPP would perform better, even with the MOM6, because we are including, you know, non-local mixing, you know, influence too as well, but it wasn't. So it turned out that EPBL seems to be better, and then in terms of you know, SSD cooling is less. But MOM6 mixed layer depths intended to be deeper than ocean high camp side. So with the KPP with the MOM6, the mixed layer depth a little bit shallower than EPBL with MOM6. So that means, you know, it will control the SSD cooling accordingly. So.
So it turned out, so before when we ran this, some of these tests initially, we used the operational version of R2OPS. And when we did that, we obtained the KPP was giving us better results. With that, we also, within that, we ran different experiments with different critical Richardson numbers. And we did the PBL, the KPP, and the KPP was better. Once we switched to the latest R2OPS parallel, the KPP was giving us storms that were too weak, and now the PBL performed better. So yeah, there are definitely differences, and that are also dependent on the initial conditions that are coming from R2OPS. Yeah.
This is Gus, HRD. This is more a question for Wallace and NHC, and maybe there's no answer right now, but it's something I want to plant this question, and it's with regards to the multi-storm. Assuming that we are limited by the grid and we can't make larger outer domains based on just what we have available right now, I mean, I want to have a conversation about what the forecasters really need, especially at high latitudes from a model like this. I mean, again, the advantages of going to a system like this, I think, have been demonstrated quite well in the past with HWRF and with HAFS now again. And, you know, if it sacrifices, you know, high resolution forecasts of ET events that are at high latitudes,
Is that something that NHC is willing to entertain? I know it would take a change in ConOps, but I think that's something that we should at least discuss.
Do you have a quick answer, or can you hold it to your discussion session in the next session? Okay, great. Thank you, Wallace, because we're out of time for this. So we're going to take our 15-minute break, and then we'll start up with the last session of the annual meeting, which will start with HPC and technology discussions with Frank Indiviglio facilitating, and then go to Wallace's NHC forecast facilitation session. Thank you.